let me record my lecture. So today, so we are talking about the beam problems, right? So we discussed the moment curvature relations, and then the normal stress and shear stress, and then we have special issue. Here, special issue is superposition. So before we talk about the information given in the textbook, so let me review the principle of superposition a little bit more. So in my okay. So I remember I explained you already the principle of superposition. You know, the principle of superposition is valid only in linear systems. This is the key point to understand the principle of superposition. So for example, let's say you have a certain structural system. So if this structural system can be, you can consider it's a beam, or you can consider this is a plate, or you can consider this is a truss, and whatever, okay? It can be various configuration. So for example, so if you apply load to your structure would behave in a certain way, isn't it? So if you apply displacement, then your structure would resist by, by generating some reaction forces. Or if you apply the external forces to your structure will deform, isn't it? So that course we can, describe that information in terms of function mathematically. Let's say we want to introduce a function, and then you want to consider your input. It can be external loads and whatever, okay? It can be external load, or displacement, or you can consider traction and whatever, or temperature change, blah, 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 many. So here, as a simplification, so I want to consider, the input is x, okay? So if you put x, then you would have your response y, isn't it right? This is a functional relation, isn't it right? So this is very general description. Let's say if you have a linear system, the linear system means, so if you plot the behavior of a linear system in two-dimensional graph, the x and y here, then, if it is a linear system, so the behavior can be described by using a linear curve, using a linear straight line. So which means instead of x, let's plug, x is x1. So if you do that, then for x1, you have response corresponding to x1. So here we want to call this as y1. So what I want to say is y1 is equal to f, the behavior function for given x1 input. Is it clear? Isn't it right? So let's imagine that you have bar, and if you apply load F1, then as the consequence of the external load, you have the displacement U1 at that point, isn't it right? And also, if you divide the load by the cross-section area, you have certain stress. So if you are interested in the stress can be considered as your response, the y value, okay? It can be anything, okay? It can be, you can consider, the various things as the input variables, and also vice versa, also for output too. And then let's consider another input. So for example, so I want to consider the x2. If you do that, if you consider x2, because of this response, the behavior, we must have y2, okay? So I'm talking about just conceptual one. So y2 is a response of the same system. So please make sure that the same system, but the input is different, okay? The input is different. So my question is, what's going to happen? So if we provide x, x1 plus x2 as input 3, okay? So if you do that, you know, because of the characteristics of linear system, the y3 is equal to, okay, mathematically speaking, doesn't matter whether we are talking about linear system or non-linear system, then I must get some response for x3, isn't it, right? For x3 here, and then, oh, sorry, x3 here. This is f, and then this is x1 plus x2, isn't it, right? Okay. But this is a linear system. The linear system means this is equal to fx1 plus fx2. Okay. This is the characteristics of linear system. So for instance, let's consider an example. Let's say we have a linear system, y is equal to, this is example, okay, 3x. Let's say x1 is equal to 2. Then what happened? y1 is equal to 6, isn't it, right? And how about x2 is equal to, for example, 3? Then y2 is equal to 9. So let's consider x1 plus x2. This is equal to 6, isn't it? 6. Then that is what? So y3, sorry, this is x3. So y3 is equal to, or if you put here 18. Is it correct? 18. And then 2, 6, 2. Oh, something wrong. Ah, sorry. Nobody told me this. I made a silly mistake. 2 is equal to 5. Okay, sorry about it. 5. Okay, then if you have 5, this is equal to 15. Okay, so if you compare this 15 with these two numbers, okay, this is equal to 6 plus 9, and this is equal to y1 plus y2. Okay, this is a simple, you know, the illustration of the principle of superposition. The principle of superposition, so-called in 우리말 중첩의 원리, that you know, that is valid only for linear elastic linear system. Okay, linear system. Okay, let's extend our consideration to, you know, more general system. So for example, let's say I have, you know, multi-DOF problem. Okay, multi-DOF problem. Then I have node 1 and node 2. Okay, then which means, so if you applied f1 here, and also we can apply f2, as the consequence, I want to calculate u1 and u2. I won't do that, isn't it, right? So which means my response, and then ui is given by, sorry, u1 and u2. This is given by the system function, okay, system of this, and then the input is f1 and f2, isn't it, right? F1 and f2. So if this is linear system means, you know, that we can do this u1, and I want to find out u1 and u2 from this structure subjected to f1 and f2, and then this is equal to u1. So I want to calculate only the u1 of, and also u2, and then exactly same system. Here I want to consider f1 only, and then 0 here. Okay. Then I want to call this is system 1. Okay, system 1. And then my u1 is u1 from system 1, and the u2 from system 1. Is it clear? Because instead of f1 and f2, I applied only f1. Then I would get some response, but only for the f1. Okay, only for f1. And then I want to do the superposition for exactly same system to make sure that the system is same. Okay, the system is same. And then here, because we already considered, you know, f1 here. Okay, f1 here. The next step we want to consider f2. 0 and f2. So I want to call this system 2. Then from the structural behavior, I can obtain the U1 for system 2, the U2 for system 2. Is it clear? Then overall response, because of the principle of superposition, U1 is equal to U1 from system 1 and then U2 from system 2. Okay? That's the principle of superposition. Is it clear? And the U2 also. U2, 1, U2, U2 from system 2. Okay? And then here I consider only the nodal displacement. Instead of nodal displacement, you can consider stress, okay? Stress. Or if you are interested in strain, it's the same, okay? This is the principle of superposition. So now let's go back to our lecture note. So if you go back to our lecture note, this is our lecture note here. So now I have a one-dimensional problem that we considered a long time ago. Okay, so we have one-dimensional problem here, one-dimensional problem. But my loading condition, so far we discussed either, if we have one-dimensional problem, either it is, the actual loaded members, okay, where we calculate the stress value. And then last time, before the Newton examination, so we discussed the beam problem, isn't it? Right, beam problem. But here, in the case of beam problem, so we have the load in the transverse direction only. In the case of the actual loaded problem, we have a load in the longitudinal direction only, isn't it? Right? But now in this example, we have the load in a very weird way. So we have the load, inclined. The loading direction is rather inclined. Okay. So now we want to use the vector decomposition. So if you decompose the vector, then we can decompose the vector into two components. The one is actual component, the other one is transverse component. Okay. So this is exactly equivalent to this inclined load, isn't it? What is the reason that we decompose the vector into the actual load and the transverse load? The reason is because we are already familiar with the situation. Okay. So we are already familiar with the situation. So if you have load in the actual direction, then we can approach the problem using the information that we discussed in the chapter for the actual load member. And then if you consider transverse load only, then we can use the beam theory. Okay, that's why. And then there's another reason. Another reason is because of the coordinate. We want to use this coordinate system. So we are indulged to this Cartesian coordinate system, the x and y, isn't it right? We really love this coordinate system. That's why, so whenever we have inclined load, then I want to, we automatically decompose load into two, the load components, the following the coordinate direction, the x direction and the y direction. Is it clear? Okay. So because of these reasons, but instead of talking about this inclined load directly, so I want to consider the actually loaded one, and then what? The transverse loaded one, okay? So now let's use another note here. Okay, so I have a bar, and then we have inclined load, okay? Inclined load. But this inclined load is what? Can be decomposed into two different load components. Okay? Then it becomes, let's say this is angle theta here. And then let's call this P. The P, the horizontal component is equal to P times cosine theta, isn't it right? And then the vertical component is what? The vertical component, PV, is P times sine theta, okay, because of the trigonometric relation. And this is equal to, so whatever happens, okay, whatever happens in this structural system is the superposition. So if you consider all the aspects one by one sequentially, then we don't miss the nature of the problem, okay? So here, I want to consider the load sequentially. I want to consider the load, the horizontal load component, and then the transverse load component one by one. So I want to consider this is case 1, and then this is case 2. Okay, 1 and 2. So here I have my structural system should be exactly same. Please look at this. So I emphasize you several times that the system should be same. Okay, the system should be same. Is it clear? Okay, the system or the function is same. Okay? I'm talking about the same system. So let's consider same system. The same system says that. So I have a support on the left hand side, and then I have this bar, and then this bar is subjected to the horizontal load component PH. That's given here P cosine theta, and this is system 1. Okay. Plus, we want to consider exactly same structural system. What I my system, okay, and then I want to consider transverse load PV is P sine theta. Okay. Then look at this. This is what? This is the one-dimensional problem, the actually loaded member. Okay, actual loaded member. And how do you calculate the stress? The normal stress is very easy, right? So once we have actual loaded member, the first we have to calculate internal force. So make sure that this is external force. Okay, the sign convention for the external force should follow that of the sign convention of coordinate, isn't it? But to calculate stress, we need to calculate the internal force, isn't it? Using the force equilibrium. So make sure that the internal force is what? Another name of internal force is stress resultant. I told you several times, is it right? Stress resultant. If you integrate the stress over the cross section, so you can obtain internal force, okay? Internal force. So here the internal force, that's why the sign convention for the internal force should be same as that of the stress, the sign convention for the stress. That if it's tensile, this is positive, isn't it, right? So here the internal force N is equal to, this is tensile, this is equal to, its magnitude is equal to PH. That's why P cosine theta. So once we have P cosine theta, then we can calculate the stress. The stress in system 1. Stress in system 1 is equal to the N divided by the internal force divided by the cross-section area, isn't it? Okay? Clear? Okay? It's very easy, right? Very easy. So, characteristics of actual loaded members, the stress is exactly the same where we measure, okay? So we have constant stress field at any point. Okay, this is the characteristics. So now let's consider system 2. In the case of system 2, this is what? This is a beam problem. Specifically, this is a cantilever beam problem, isn't it right? The cantilever. To solve a cantilever problem, to calculate the stress, the relation between the stress and bending moment is what? Stress is equal to the bending moment times what? The position y coordinate divided by second moment of inertia. Yeah? So we want to use a flexor formula. Sigma 2 is equal to minus bending moment y coordinate. If we want to calculate the stress here, for example, the stress is linearly distributed and divided by the second moment of inertia here. Then let's calculate the bending moment. The bending moment diagram look like this, isn't it? So this is equal to this triangular. This is equal to PB times the length, isn't it? Right? PB times the length. So obviously the bending moment is changing. Function of x coordinate. It is maximum at the left corner, and then the bending moment is equal to 0 on the right corner. Okay? Yeah, it's changing. So we can calculate the stress. Here the stress in the second system is function of x position and also the y position too. Look at this. So my bending moment is function of x coordinate, is it right? Is it? Yeah? Come on. My bending moment is function of x coordinate. And then also it depends on the y coordinate too, divided by the second moment of inertia. That's why my stress in the second system depends on both x and y. Okay, x and y coordinate. Then my stress in my, the real system is stress is equal to sigma stress from the system 1 and stress from the system 2. Clear? Okay. And then here let's look at the feature a little bit more. In the case of stress from the system 1 is what? It is what? Constant, constant. Doesn't matter at any point, okay? It is same here, and also here and here. But stress from system 2, it depends on the coordinate, isn't it? It looks like this. Compression and tension. Okay? So that's why if you superpose, so we have what? If you superpose, oh, by the way, the stress distribution from system 1 is constant. Then if you superpose these two, then what happens is, the origin of the stress distribution in the system 2 is shifted toward the positive side. So for example, it becomes, my stress distribution look like this. Because of contribution of this, we must have less negative stress part and more positive stress part. Is it clear? Okay, so overall behavior shifted to the positive stress scale. Now how about let's consider another example. Let's consider bar here, and that's subjected to the external load, the pair of load, and at the same time I have torsional moment too. Okay, torsional moment too. This is equal to what? This is equal to the actual loaded, one actual loaded member, and then one torsionally loaded members. Okay, so obviously the stress condition here, the first problem, so we have only the normal stress. But in the case of torsional problem, so we have pure shear stress condition, isn't it? Is it clear? Yeah. Here the stress is equal to normal stress divided by cross-section area, and then here shear stress is equal to torsional moment and the position measured from the center of the cross-section divided by second moment of inertia, polar moment of inertia, sorry about it. Then if you superpose these two, the stress condition for this, we have both the normal stress and then shear stress. Okay, this is the principle of superposition. Do you have any questions for this principle of superposition? Usually in undergraduate level and then even in graduate level, this principle of superposition is very, very useful. Even for your design procedure. Have you ever heard about load cases? I wonder, 4학년 있어요? 4학년? Okay, if you study design, if you take design courses, you you discuss the concept of load cases. So we consider individual, load cases, and then we superpose the load cases to obtain, the various combination of load. Okay, the principle of superposition is widely used even in real engineering, actual and real engineering practice. Okay. All right, so now let's talk about the stress concentration. So make sure that, so far when we discuss the beam problem, look at this. Let's say we calculate the stress field here. So there is no hole. So if there is no hole, my stress field would look like this, okay? So we call this nominal stress. Nominal stress distribution. So-called 공칭 응력 분포. So nominal means we don't care about what happened inside, okay? So we want to check, overall stuff of penalty. Okay? I don't care about what happened inside. But unfortunately, if we have a hole, then I have certain, stress concentration here. Stress concentration. So in the case of nominal stress distribution, we do not consider any stress concentration near the hole. Okay. So we have, if you remove some part of cross section, then my stress increases little bit, but in beam theory, we cannot calculate stress concentration. So when we discuss actual load members, and we also discuss stress concentration, if we have any abrupt change of geometry, then we have stress concentration. But here is same, okay? The even in beam problem, so we have to consider stress concentration. So for example, let's consider a larger hole. So if you consider larger hole, then in beam theory, we consider only these two material segments, okay, material segment. Then we calculate the second moment of inertia, the whatever, blah, 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 okay? We calculate the stress field, linear stress field. So in beam theory, if you calculate the stress field, we have this linear stress field, okay? Small, let's use new page, yeah. Okay, say I have a beam cross section, okay? Let's consider a hole. Then I want to consider this cross section A and cross section B. So if you consider cross section A and A, then I have, solid segment, isn't it, right? Then I can calculate the stress distribution. Then, for example, if I calculate second moment of inertia, so I would have this stress distribution, isn't it, right? But if you consider the B, if you do that, then this part is missing, isn't it, right? This part is missing. That's why we have, the actual segment here. So obviously, if you calculate second moment of inertia using this section, it should be smaller, isn't it, right? The stress distribution should look like this. Stress should be greater than, the cross section A and A. Okay? But in addition to that, we still have what? Stress concentration. And then this is nominal stress distribution. Okay? Then how do you calculate the stress concentration? So of course, it's similar to before, okay? So we use handbook, okay? We don't have to worry about it, okay? So we can refer to the handbook. So for various geometry, they already calculated, the stress concentration factor. That's why you don't have to worry about it. So the only point that you have to pay attention to is that, there is a certain stress concentration factor, okay? The maximum stress is not the same as the nominal stress that we calculated using the beam theory, okay? The stress distribution that we calculate using the beam theory is called nominal stress. Here is sigma and NOM, nominal stress, okay? And then the maximum stress should be multiplied by, stress concentration factor for the maximum stress value, okay? So here, then let me stop my chapter 5 for the beam stress, okay? Do you have any questions? So of course, if you have any questions, you are very welcome to send me, your questions to this email address. Okay, so you guys are very welcome. So, when I notice your questions from emails, I'm very happy to answer to your questions, except questions regarding homework. For example, when is the due date for the homework? And that's, certainly is not my part. Okay, you should ask to my TA. Otherwise, for the theories and the lectures, you're very welcome to ask me questions via email. Okay. So here, let me take about 10 minutes break.